So let's talk a little bit about epochs. Let me start by saying there are people in this room who know way, way more about epochs than I do. So if you ask any questions that are beyond my expertise, I'm going to defer to them. What I do claim to know a little bit about, and I think even in this I'm exceeded by people in the room by a long ways, is using Python and epochs together. So what I will try to talk about is epochs and beamline controls, how Python and epochs work together. I'm going to talk specifically about the CAUtil package, which is sort of intimidating since the author is in the room. I'll talk about accessing PVs and what those are in that routine. Dealing with what I'm going to call epochs dropouts, and some tips that I've picked up in terms of writing beamline code, a few of which I don't follow, as Matt can tell you. All right. Okay. So the BCDA standard, such as it is that we use a communications protocol called epochs to control our beamline equipment. We also use epochs to control the ring. And what epochs does is it's basically a communication standards. It takes the information that we want to express and sends it to all the various beamline devices like motors and scalers and stuff like that, and vice versa. It gets the information back. We can run epochs. We can talk to epochs a lot of different ways. We can talk to it with the MEDM protocol. The MEDM protocol, you'll see some screens from, generates nice screens that we can push buttons on. We can write spec scripts, and we can write Python scripts. And there are many other ways of controlling epochs, but the one I'm going to concentrate on is writing Python scripts. Python has some advantages. As you guys have seen, it's a really fully featured programming language. As you saw yesterday, you can create nice graphics really quickly, really easily. As you will see someday when I get around to it or somebody else does it, you can generate graphical user interfaces, I won't say easily, but quickly and without too much trouble. If you can stick in database calls, you can do higher level math, as we'll be talking about once we finish talking about epochs. Okay, so I can't do justice to what epochs is or what it does, but we can talk a little bit about it. From my perspective, epochs is just simply something that sits in the middle somewhere of my beamline and ferries information from one place to the other, and it the information starts either, let's say, at my computer, and then it goes to something that actually does my controlling, the epochs controller, which is known in epochs parlance as an IOC, and I forget what IOC stands for. Input-output controller. Oh, obvious. Okay. The input-output controller, the IOC, then talks to my various devices. Okay. When I talk to epochs, I do that with a protocol called channel access, and the way that, for my purposes here, all that channel access is going to be is there's a little variable sitting out somewhere which I can either write to or read from. And when I write to it, epoch's job is to take that information and bring it over to whatever it is it's supposed to do with that. And if I read it, it's supposed to reflect whatever the current status is of whatever that's connected to. So you can normally only communicate with these variables, which we call process variables or PVs, on an IOC that's local to your beamline, except that there are some IOCs that will either get from the ring to you or get outside of your beamline because they're repeated on a PV gateway. And you'll see a couple examples of some things like that. When you talk to the IOC, it's going to happen via Ethernet. When your IOC talks to the various device that's connected to it, it may be talking via the VME connection in the VME crate. It may be going via Ethernet. It might be going by Pony Express, for all you know. And the beauty of epics is that you don't have to care. That every PV that you talk to looks like every other PV that you need to talk to in terms of how you do communication. Okay. So how do you talk to epics when you're in Python? Well, there are a bunch of different ways, but I'm going to highlight two of them. And one of them is this package called CAUtil. CAUtil is found on all the XSD beamlines at present. It's supported by BCDA. It's on all well, not all beamlines have APS share mounted, but all beamlines that have APS share mounted have access to this. And but I will point out that CAUtil is not likely to be updated past Python 2.5. Fair statement? Okay. There is another new package which looks really nice. I haven't had the chance to work with it yet, but Matt Newville has written something called PyEpics. And I've got a web address here for it, and Matt did a nice talk for the Python interest group, which you can go grab the PDF from. I guess if you're inside the APS firewall. If you're not, send an email to Debbie, not me, and she'll get it to you. PyEpics is not yet supported by BCDA, but I think it probably will be. Is that a fair statement again, too? Okay. All right. Okay. So I'm going to talk about talking to epics with three very simple commands. One is called CA_get, that reads a process variable. One is called CA_put_w, that writes to a process variable and then waits for the action that you've asked for to happen. Or you can do the same thing asynchronously. And if you do it asynchronously, you send the value, but you don't wait for it to finish. So for example, I have code that you start a motor moving, and then while that motor is moving, you go off and do something else. So you don't wait. You can get other things done while the motor is moving. So for the second case, where I just want the motor to move, I don't want to wait for it to get to its position, I use CA_put. But if I want that motor to move, and then I want to wait for it to get there, and then I want to do something, I use CA_put_w. This isn't all the communication you can do in epics. There's plenty of other things you can do. For example, you can monitor a PV, which will write out or do something every time the value changes. You can have alarms. When a PV gets to a certain value that you want to trigger something, it will do something. You can have other types of callbacks where once something is triggered, something in your code will go. You can do all that stuff, but I don't. And I've found for my purposes, everything I've needed to do in epics, I've been able to handle with this. So that's what I'm going to cover. There's another reason that I have for only covering these things here, and that has to do with these two different packages. If you write only CA_puts and CA_gets, then your code will be very transportable between CAUtil and PyEpics, so you won't have to change it very much. And I can envision a way that we won't have to change it at all. So that will be to your advantage. If you're going to need more features than these CA_put and CA_get and actually it's put_w, not get_w, I recommend that you start directly in PyEpics, even though it's not yet being supported. IT and BCDA all have to figure out how to get it onto your computer. But if you can get by with just put and get, then I suggest you start with CAUtil. I recognize this is a moving target. 6 months from now, this may be different. But, and as I said before, if you only use these routines, it's going to be pretty easy to move from CAUtil to PyEpics when or if that happens. Okay. So moving forward, I'm not going to talk about PyEpics because I haven't used it. But in terms of CA put and CA get, it's pretty similar. So assuming you have APS share mounted on your beamline, which will be true if you're in XSD, if you type APS share bin Python, you'll bring up a Python shell, and all you have to do is then type import CAUtil. Okay? Well, that's the way it should work. What I've found, and maybe this is just 11BM, but I suspect there are other people out there who will find this as well, is that you might get an error like this. And if you do get that error, it's because there's some out-of-date environment variables that are lingering around due to setup files. And here is what those environment variables are that are causing the problem. Probably something that could be chased down and just fixed. But often I'm just interested in getting my job done. So here's the workaround. If you're working in Bash, you can overwrite the variables using export and then start up Python. And if you're a real Bash aficionado, you'll recognize that you can just put Python path equals Python startup equals, and then you don't need the export if you do it all on one line. Okay, for CSH or TCSH shells, the C shells, you have to do it in 3 lines, and you do it this way. Okay, so this will be in your notes if you have the problem. Okay. Another thing you may need to do, depends on what you're doing, when you read from a process variable, very often it's just one little bit of information, a temperature or a motor position or something like that. But that's not true for everything. And some Epics process variables can be attached to very big buffers. And as an example, on 11BM, we have a struct scalar card in our VME crate, and that will contain our entire scan, which might be 10,000 points, 100,000 points or more. In order to read that much, I have to, ahead of time, give Epics that much buffer space. Okay, so you do that by setting an environment variable, which is either done in this flavor or this flavor, depending on which language of shell you're using. and you need to do this either before Python is started, or if you're sophisticated, you can start up Python. You can set the environment variable inside Python using the the OS routines, but you have to do that before you import CAUtil. So you don't actually have to do this with at the shell. So enough of this. How do you actually read a PV? Reading a PV is really easy in CAUtil. You've imported CAUtil. You type cautil.caget and then the name of the PAV, and you get back the value associated with the PV. The value you get is going to depend on what type of process variable it is. This one is reading a motor, so I get the motor position. This one is reading a string value, and it gives me back a string. Okay, this one is reading from my MCA and my actually multi-channel scalar, and I get back a array that it was too big to print out. Okay, so the information you're going to get from a CA get is going to depend on what type of PV you're reading. That's not a problem because you're not going to be reading PVs at random. You're going to read a PV for a particular purpose. Setting a PV is similar, except now we specify a value. So it's either CA put or CA put wait with a PV name and a value. So here's an example of some real live code. when I want to drive the 2 theta motor on 11 BM, I call this routine, and I give a position. The PV corresponding to the 2 theta position is right here, and I either, if this routine is called with a wait, then it's going to drive it and it's going to use a CA put W. If this routine is called and wait is false, it'll start it driving, but it won't wait. Okay, and so if I call it and wait is false, it's going to run this thing very fast and come back right away. And the motor will keep moving, and it'll keep moving until it gets there. That may or may not be what I want it to do. In fact, what I do, the way that I'll typically use this is if I'm calling it and I know that I've got more things to do, like for example, I'm going to drive the 2 theta arm, and then I'm going to go talk to the robot. I'll set it going. Then I'll come back and I'll call it again, sending it to the same position, this time with a wait. If it's gotten to where it's going to go, it's going to respond very quickly. If it's still moving, it'll just wait at that point until it gets there. Yes, you can do that too. But this is very simple. That requires some thought. But yes, you can actually do that too. But here's my warning. Okay, they don't always work. Okay, when you do CA put or CA get, you may or may not get what you want on that try. Why is that happening? Well, lots of reasons. When EPIX was set up, it was set up to say, okay, this is a mechanism that we use for communication, and we want it to run very quickly. We don't want to always ensure that messages actually get to where you sent them to, because we want it to run quickly. And you don't want to have potentially a long delay because of some problem. But sometimes your connection in EPIX may not go through for one reason or another. Sometimes EPIX will get the message and it will send it off to your device, but because your device is connected by RS-232, which is a lossy mechanism as well, it doesn't actually change your temperature or whatever it is that you want to happen. So when you write a script, you should consider that you may get an exception. Nothing's wrong, but it just didn't do what you wanted, and it's going to generate an exception and it expects you to try again. Okay? It doesn't do that a lot, but it does happen. It may run normally, but it may not have done what you wanted it to do. Okay, so if you're writing a script that does 4 things for you, and you'll know immediately if it doesn't run properly, then you don't have to worry about it, because you'll just run it again. Okay, but if you're writing some Python code, and you want that code to run over and over again, and you don't want it to fail at 2 in the morning, then you need to think about these things. And what I'll say is you need to code defensively. Okay, it's not that EPIX is problematic. It's just that it doesn't work the way I want it to work. I think I'm quoting you directly, Pete, on that one. Okay, so defensive coding. How do we do that? All right. We have a filter box shutter that we use to block the beam on 11 BM so we don't irradiate our samples when we're not actually collecting data. Here is a bit of code that's used to open the shutter. So what do? I start a loop, and I'm going to try it 10 times, and then I have a try statement. And then first thing I do in my try statement is I read the process variables associated with the 2 flags, and if they're in the if they're in the open state, then this one will be 1 and this one will be not 1, and I return false. So I've asked it to open the shutter, and if the shutter's open, it just returns false. Okay, if that's not true, then I send a 1 to this process variable, which tells it to open the shutter. Then I go to sleep for for a second and a half. Why? Because the PV's the shutter isn't going to open instantaneously. I need to give it a chance to send the message, and then because of the way that this particular communication works, because it's going via RS-232, I think about every half second it reads back to see what the status of the filter box is. So I need to wait a little while. Okay? So if all of these things have worked properly, then the accept clause isn't going to go, and it's just going to loop again. So then it's going to check the status variable again. And if it's still not open, it's going to do it again. So this thing is going to loop, and it's going to loop up to 10 times to try to open the filter box. And if it doesn't succeed in opening the filter box, it's going to return true. Okay, we'll talk about why true and false in a moment. Now, what happens if, in the process of this communication, EPIX throws a exception? Now, in this case, it's one of the few cases where I'll break my own rule, and I'm going to use try on every possible exception that I might have, because I really don't like getting woken up at 2 in the morning when the diffractometer fails to open the shutter. I'm going to have it, if any one of these 2 or 3 CA gets and CA puts fails, it's just going to go right over here to this accept, where it's going to print out a message so that if I find out, I can at least see that it happened. And it's going to sleep for 1/10 of a second. It's going to try again. And it's going to keep trying again up to 10 times until it either gets through or it gives up. Okay? So I personally, and I don't think that this is anything worth recommending, but I personally use a convention where in my instrument control routines, they return true if there's an error, and they return false if things are successful. And the reason I do that is then I can do something like this. I can say, if this is inside routine, do something, then I can just simply say, if do something. And if that comes back true, then I've hit an error. What am I going to do? Well, I might log it. I might quit. I might send off an email message. I might trigger another exception so that I get to my outer error handler or something like that. But that's the way that I tend to write my code. Question? Yeah, yeah.
When you would do that CA put W,
right.
it is possible that for whatever reason, if that process is not going to go anywhere, you're going to just sit there and wait forever. Shouldn't you just do CA put on that?
That would be perfectly legitimate. I don't think I've had a case where a CA put W has hung. Can anybody who's got more experience with EPIX comment on that? We'll see it. Yeah, Tim? It's not that long. It's not. I think it may be 60 seconds or 5 seconds or something like that. It's not a very long timeout.
If it kind of hangs, then it throws the error?
Right. It'll throw an exception. Yep. Yep. So the question was, could this CA put W hang? And the answer is no, it will not hang. It will wait as long as the timeout period is, and that's something that's configurable. Okay. But you're absolutely right. As I look at this code, I would probably have just put a CA put there. That's the disadvantage of copying my own code, as I show my mistakes. Okay. So I'll come back and I'll probably I think I've got some other examples where I do some defensive coding. Now, you'll notice here I send a CA put and then I wait. An awful lot of my code does wait. Waits for things to happen. And yes, you can avoid that by using callback routines. In general, I don't recommend that because it's a lot harder to write that kind of code. It's a lot easier to think, do something, wait for something to happen. Do something, wait for something to happen. If you're really sophisticated and you want to wait for multiple things to happen, yeah, you'll need to get into callbacks. But it's a lot more difficult to do that, and to do that right is even more difficult than that, because you need to think about what happens if two things happen at once. What if things don't happen in the sequence that I'm expecting them, so on. Okay. So as I said, you can use callbacks, but it's complicated. If you need to have code that works really, really fast, you do something and you want to get a response right away and do something else in your computer. So you want to do things, 10 times, 100 times, 1,000 times a second. You can't really do that effectively with weights. But that's not typically the case on our beamlines. So if you want to do a response that's on the order of 1/10 of a second or something like that, or longer, or it's going to be longer than that, then you can use this time.sleep function. But as you're going to see when we start doing GUI programming, when you're sleeping, your GUI can't respond to anything that's going on, okay? Because you've hung the computer effectively. It's not using any CPU time, but it just can't do anything else. So you don't really want to use long time.sleep calls. So this is what I do, okay? You might have seen before, here we go, GUI.sleep. What GUI.sleep does is it does this, is it breaks up the sleep period in tenths of a second. And then every 1/10 of a second, it calls this wx.yield. And what that does is that gives the graphical user interface a chance to catch up on anything it needed to do every 1/10 of a second. 1/10 of a second was chosen somewhat arbitrary, but it's a long time to a computer, so it's not doing this very, very often. And it's a short time to a human being, so that when you click on a button, you may notice it didn't respond instantaneously, but it's damn close to that. Or if you've uncovered a window, it pretty close to immediately responds by repainting the window or whatever it needs to do. Okay. So let's talk a little bit about alignment programs, because that's something that I think a lot of people might want to use Python for. You can use the scan record to tell a motor to advance over some range of steps and come back with a series of counts. You can do that. I used to do that. I don't do that anymore. I don't do that anymore because what I would find is that I would start a scan going, and then I found my peak in the first third of the scan, but it's going to keep going anyway. Or even more frustrating, I found my peak, but I didn't quite get to the top of it. So then I know better where to start scanning, but I have to go do another scan. So when I do alignment programs these days, I do something like what this code over here does, where and this is sort of, since sort of more pseudocode, I have an outer loop which says repeat, and that's there so that I can just trigger go do this whole thing again from the beginning. So it's going to keep running this loop until I decide to make repeat false. I set the values for the position and intensity array to be 0, and then I have another loop that's going to go forever, or we'll see, and it says, okay, move to wherever I'm going to be on X for my current scan. And this will return true if I'm out of range. Okay, if I've gone too far and I haven't found my peak, it's going to trigger an error right here. But otherwise, if this returns false, then everything is fine. That's my convention, not necessarily yours. And it's going to go do some measurement. So it does a measurement, it comes back, and it sticks my current measurement value into my Y list by appending it. Then I look to see, have I got my peak? Am I done? Okay, if I've got my peak, then I'm done. I can set repeat to false. I can break to get out of here. I've got my peak. I'm done. So I don't have to go any further than I want to. And my check peak routine and or move scan location peak routine are the things that decide, you know, should I keep going or not? And maybe where I should start and maybe where I should restart. And if check peak comes back and says do a restart, then it resets my scan range, which could have been done inside here since I'm passing it. Break, but I haven't set repeat to be false, so it's just going to start repeating the scan again. Okay, so that's the way that I approach doing alignment scans. But one of the things, depends on what kind of system you're looking at. There are probably better ways, particularly on things that take motors that take a long time to move, but are reproducible, perhaps because they have you're going to work against an encoder, or perhaps where you need to do alignment scans of 2 or 3 different positions at the same time, where the fastest way to do things may not be scan one motor, scan another motor, scan a third motor, and optimize those, then go back and do everything again. Those are real minimization programs, and I think that there's a real need for people to think about multi-axis alignment capabilities. How you're going to do that's going to depend a little bit on what kind of positioning and alignment you're doing. It's going to be different for a PZT, where you can send it someplace, move it somewhere else, and go right back, versus a motor where there could be some hysteresis and things like that. But nonetheless, if your counting time is long, or your alignment time is long, movement time is long, then there are probably better ways of doing these things than just doing lots of nested scans. Okay. All right. Well, we've talked about PVs. We've assumed you know what all the PVs you want are, but if you may not, I recommend the first thing you do if you start working with Python, before you start doing Python scripts, you sit down and you start playing at the console to try out what you want to do. And as you're doing it, you can keep notes as to what you're doing. So let's talk about how you get to find out those PVs that you're going to need. Well, first thing you can do is if you go into the MEDM screen that your system has, then if you use the middle mouse button on any of the widgets in the MEDM screen, you'll get from MEDM the name of the process variable. Okay? And if you hold that down and slide it over to some X11 programs, not all, but some X11 programs, it'll even capture that name for you. Now, Tim mentioned to me there's something out there called name capture, but I never found out where you get to that, how you use it. But I'll refer you to your local BCDA beamline specialist, and they can help you with that. But that's not all. If you press the right mouse button, that's the one you normally don't press, and click click anywhere on the MEDM screen, you'll get this menu here with a bunch of different choices. And the one that I find I use all the time is this PV info. Okay? And that's what PV info will pop up for me when I then, what PV info will do is it'll change my mouse cursor. I can then click on a PV, and in this case I'll click on this one here, and it tells me a lot of useful information. It gives me the name of the process variable right there. It gives me some descriptive information. I don't usually use this too much, but it tells me where it is. So this process variable here is not on my local beamline. It's actually talking to something on the gateway and connects back up to the ring. But it tells me something that's very important, which that it has 2 potential values. 0 means waiting, and 1 means opening. Okay? So that tells me when I read this process variable, I can expect to either see 0 or 1. Okay. Okay. Most common thing we want to program are motors. So let me tell you a little bit about motors. This is the 2 theta axis on 11BM. So there are lots and lots of PVs associated with motors. As Lynn mentioned a moment ago, there's one that will tell you whether motor is moving or not. Where will you find it? You'll need to press more, and maybe more again, to get to a screen that has all these process variables that you might want to access. The most important ones are where is the motor and where do I send it. You can read the motor value from this guy right here, and that's got .rbv, and you can send it by specifying the value that goes in here. So if you use CA put to set this value PV, that sets the motor moving. And if you use this CA get to read this value, you'll find out what where the motor is, or at least where the motor controller thinks the motor is. Why not? Might that not be the same as where the motor actually is? Well, the simplest reason may be that you never turn the motor on. Another possibility could be that if the motor stalls and it doesn't have an encoder, then as far as the motor controller is concerned, it sent it to that position. The fact that it hasn't gotten there, it doesn't know anything. It just knows how many pulses that have been sent. But there's lots more information that you can get by going to the more sophisticated screens. So Matt commented that it's really nice sometimes to drive a motor to its limits, to its soft limits, and you can look up and read what the soft limits are by finding the appropriate PV. Okay. So how do we use the PV? Well, I showed you a little bit before about setting the PV, but I left some stuff out. So when I'm working with reading 2 theta, I set up my code in such a way so that if I hit a error on an exception on reading the 2 theta value, it's going to go back to some previous part of the code, but it's not going to crash out. So I don't need to worry about handling an exception here. But when I drive 2 theta, I want to be careful. I don't want to go past the place where I'm driving 2 theta without having 2 theta where I really want it to be. So that I put in a block, and a block to trap the exception and to respond accordingly. In other cases, I'll do what I did before, where I'll not just trap the exception, but I'll also loop until I get there. Okay. Now, talking a little, yeah.
The CA put will throw an exception if you try to run it outside the limit switches, outside the soft limits?
I don't believe so. No. No.
How are you going to figure out that you try to drive it somewhere where it cannot get?
I won't from that code. In this case, it's my job to figure that out. I can.
In this case, the only exception it's going to react to is if it cannot write in that .val place.
If it can't write, yes.
So that's the only exception you're catching.
You know what? I would tell you this is one of those things you should go try out on your beamline, because I don't guarantee.
So like crash my hardware and your hardware.
Right. 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 Yeah, I don't want you crashing my hardware. But I'm pretty sure that it does not throw an exception if you try to do that. But I would never have driven my motor out of bounds anyway, so I wouldn't know. I've never done it. Okay. Not all PVs are as simple as motors, and I brought up this one here. This is our sample changer, aka the robot, which my wife calls Snookums. Has a more sophisticated set of PVs associated with it, but again, by using it in MEDM, we see what we need to do. So the first thing that we will do when we use this is we'll tell it what sample position we want to load. So that's this PV here, mount val, MNTVAL, and then the next thing we do is we press the button. So that's that PV there, mount request. Once the robot has loaded the sample, it reads the barcode number off of the sample and it sends it over to here, Oops, I'll get back to that in a moment. But that's how I load the sample. When I write my code to do this, I need to do two things. I need to first set a value for this PV, and then I need to set a value for that PV. So here's the code that will do that, the most basic code. Okay. I put the position number that I want into the first PV, and then I trigger the mounting. And how did I find out that I needed to do it this way? Well, I found out I needed to do it by trying it. And I found that it worked reliably if I put a 0 in and then put a 1 in. And that change triggered the mounting. I'm not 100% certain that that 0 is required, but I can guarantee you that it works this way, having exercised it enough. Okay? However, again, I want to know when I send that command in that something's actually happened. Okay? Because it is conceivable that the information gets to EPICS, but it doesn't actually get the motor control, the robot controller, to do something. So when I'm looking at this MEDM screen, I might ask myself, what is it that's going to change? Well, what will change is that this barcode reader should pop up a barcode. So there it is, the PV is barcode. So I will use that to check that the robot's done something. So when I put all that together, and I might also check something else. Before I started mounting my sample, this is going to be green, meaning there's no sample mounted. After I've mounted a sample, that should be yellow, telling me that the sample actually got mounted, which it reads by noticing that something's blocking a little light beam. And that's a slightly different kind of PV because here I'm reading a bit value. But it doesn't matter. All I need to know is that it's going to give me either 0 or 1. Okay, so here's some code that I would use to check if a sample was mounted. Again, I loop up to 10 times. I try to read the bit value. If it tells me the sample's mounted, I return false. If otherwise, it returns true. And it's going to keep trying to do that until it succeeds or until it gives up. One of the two. Okay, so this is where life gets a little complicated. How do you deal with the fact that things may not work? Okay, so here's some code that I work with to work with things. So what I'll do is actually this is to load a sample. I don't know why I use this. Okay, so first thing I'll do is check if there's a loaded sample. If there's already a loaded sample, I can't go on and load a new sample. Then tell the robot what sample number to use, load the sample, and keep trying to do this. So why do I, and if any one of these things throws an exception, I go back to the beginning and do it again. Why? There's no problem in sending the position more than once. Okay? But this code will actually give up after a certain number of exceptions, because I don't want it to keep talking to the robot, and do it 1,000 times. I'll usually say 10 times. If it fails 10 times, then I really do have a problem. It's time to get a human. All right. Now, one thing that I've done all the way through my code, which I don't recommend, but I must admit I've done, is I hard-coded my PVs into my code. And that bit me once because Matt decided to change the way that he handled, I forget what was it. That's right, when you change the sample stage, all the PVs related to the sample stage changed. So that meant I had to go through the code and find all the places where the sample stage was referenced and change all of those. And the worst thing could have happened was I could have missed some. So it's better to define all of your PVs in one place. So here, how would you do it? There's lots of ways you can do it, But my recommendation would be to define a dictionary, define a symbol that you'll remember. Okay, drive 2 theta, read back. I'm sorry, diffractometer 2 theta read back, diffractometer 2 theta set, and those are the PVs for them. And then you write your call to look it up in the dictionary. If you do that, you'll spend a lot less time changing PVs because all your PVs are defined in exactly one place. That goes in the category of do what I say, not what I do. Okay, other tips. When I work with EPICS control codes, I'm typically working with a lot of different screens open, trying things in different ways. I'll have the MEDM window open. I'll have another one open for just getting the PVs in the next window. I'll have a Python shell where I'll try out commands. And I'll have an editor for what I'm actually writing so that once I get a Python command that I like, I'll copy it over from the Python shell over to the editor so that I can keep writing my script as I go, and then I'll try out the script in small sections. A couple things that I'll mention that are worth your time knowing about in the context of writing for beamlines. You don't want to just record your measurements. There's this wonderful term called metadata. Metadata is everything else you know about your experiment other than what you actually measured. You want to keep track of as much of that as possible. A good way to think about doing this is with hierarchical storage. So there's a hierarchical format called Nexus or HDF5 have nice Python interfaces. Logging is a real good thing. Printing out an error message to the screen isn't real useful because the screen may not be there when you want to see the error messages. Consider putting them in a file. And while I don't use this myself, there is a nice logging module built into Python. The other thing is that if you don't know anything about using databases, you may have a tendency to reinvent the wheel. I know I've done it many times, except most of my wheels are square. MySQL is a wonderful free database. Python talks to it really well, and I recommend when you're thinking about beamline code that databases are a good place to get the information you're going to need to run your instrument, and they're a real good place to put stuff that you've measured as well.